Hello everyone, welcome back to ptet.chemistry channel. My name is Dr. Art. In this tutorial video, we go through these AQA topical A-level questions. So these are suitable for any 16 to 18 years old students around the world. These are questions that are based on the AQA A-level syllabus. So in this first one, we have these elements in period 3 of the periodic table. So that's all the way from sodium to argon. So state the element that has the highest melting point. So we're going to know the series of the elements in the third period in terms of melting point. We know that sodium all the way to aluminium will have stronger metallic bonds due to the factors affecting the metallic bond. Where the cations get smaller, there are more electrons that get delocalized from the outer shell. And then of course there is also the size getting, well, I already mentioned size getting smaller, charge getting bigger, as well as the charge size, as well as more electrons that get delocalized. And now we are moving on to silicon, which is just below carbon. So silicon is actually the element that has the highest melting point as a result of its giant covalent structure. So we talk about giant covalent structure, and in terms of the giant covalent structure, what do we need to break for melting it? So melting silicon, melting it requires a large amount of energy, or a lot of energy, because we do need that to break the many strong covalent bond. So the key focus here is, what do you use a large amount of energy to do? We are breaking many strong covalent bonds, and these are extensions of the concept you have learned at IGCSE or O-level chemistry. And this is covalent bond between the silicon atom, of course, because in the structure of silicon, just like in diamond, each silicon is bonded to 4 silicon, and then in turn, each silicon again is bonded to 4 other silicon, something like that in the giant covalent structure. So just to continue the story, of course, it goes all the way down to your phosphorus. So your phosphorus is P4 as a molecule, goes up slightly to S8 because there are more electrons and therefore stronger van der Waals forces, stronger induced dipole or temporary dipoles between the molecules. And then it goes down to CO2, and of course finally it goes down to argon, where argon will have the least number of electrons in the outer shell. Not the outer shell, the least number of electrons in the molecule. So in terms of the strength of van der Waals, or the strength of induced or temporary dipoles, we know that that is to do with S8 being stronger than P4, being stronger than CO2, and in turn that is stronger than argon there, because there is greater total number of electrons in the molecules. Well, anyway, the question is not asking you on the rest of the elements. Regardless, we still need to know the trend of the melting point across the third period. In part B, this is about the element that has the highest first ionization energy. This is across a period. So again, I'm going to quickly sketch out what is the trend. In general, the first ionization energy will increase, but then it will drop between the S and the P subshell, and then it will go up again, and then it will drop again when you go from P3 to P4 for reason that we will explain in a little bit. And then it will go all the way up to your noble gas, and then it will go all the way down when you go to the new elements. So across the third period, that is sodium, and then the new element in the first shell, in the first group 1, that is going to be potassium, just below sodium there. So as mentioned, the first drop there is between the S and the P subshell. So that is going to be your magnesium going to aluminium, the first drop. And the second drop is between your P3, the third element in the P block. That's going to be between your phosphorus and your sulfur due to the paired electron repelling slightly more than the unpaired electrons. Therefore, slightly easier to remove from the sulfur for the first ionization energy. You want the highest, so the highest there is going to be this noble gas at the end there. So that's just going to be argon. So the element is argon. So across a period, so this is about the fixed assay. Across a period, then we have more number of protons first. So number of protons increases, so therefore nuclear charge increases. So that's our first point. Nuclear charge is referring to the charge of the nucleus, is referring to the positive charge of the nucleus that will become more and more positive. But then we also know that shielding is roughly constant because the electrons are filling in the same shell. So shielding is roughly the same. because electrons are filling in the same shell, which in this case is the third shell. And last but not least, we talk about the net attraction that your outer shell electrons feel. So overall, the net force of attraction between the outer shell electrons as well as your nucleus is going to get stronger, and the protons in the nucleus get stronger, and if that gets stronger, so therefore we can say that difficult to remove or more difficult to remove, and that is why argon at the very end there with a fully filled outer shell, that's going to be the most difficult to ionize there. Part C suggests the element in period 3 that has the highest electronegativity value. Electronegativity is defined as the power or the ability of an atom to attract bonding electrons to itself. So this is going to be not fluorine but actually chlorine, because we know fluorine is the most electronegative element in the whole of periodic table. It decreases downward, it decreases from right to left, so going across a period electronegativity increases, and therefore across the third period you expect it to be chlorine, not argon, because argon is a noble gas, so meaning to say they don't like to form a bond at all. In part D, this is about the electron pair repulsion theory. In the syllabus, it's called valence shell electron pair repulsion theory, VESPR, VSEPR. So we have ClF3. The easiest thing to visualize it is actually to try and draw the display formula. So fluorine, there are 3 of them, which means the chlorine must be the center. Fluorine is group 7, so therefore they will form single covalent bond as they share 1 electrons. Second period element share 1 electrons, group 7, to complete the outer shell. Chlorine has 7 outer shell electron, it shares 1, 2, and 3. Therefore, you still have 2 more on the chlorine. So the shape of ClF3 is actually going to be a T-shaped molecule. So draw the shape. So the shape is essentially looking exactly like that. And then you got the 2 lone pair. So this is called T-shape. So the T-shape there basically is a result of 3 bond pairs and also 2 lone pairs on the chlorine. So that means the lone pair repel more than lone pair bond pair, which in turn repel more than bond pair give me the T-shaped molecule. How about CCl2? If I draw CCl, it looks like that. So basically the chlorine is group 7, they share 1 electron to complete the outer shell. Now the carbon is group 4, it's got 4 outer shell electrons. You only use 1 and 2 for bonding, so naturally I still have a lone pair on the carbon. So that is 2 bond pairs and also 1 lone pair. So the shape doesn't look like that. By the way, the shape doesn't look like that. So in fact, the shape is going to be bent or non-linear as the lone pair there try to push the bond pair away. We're looking at lone pair bond pair repelling more than bond pair. Didn't ask for the bond angle, but the bond angle is roughly going to be around 117, 118 degree, just below 120 degree. The shape there is actually what you call non-linear. Can call it bent as well. It's a different bent with water because water has got 2 lone pair on the oxygen. So name the shape non-linear or bent geometry there. Okay. Now last but not least, write an equation to show the formation. This is a standard enthalpy change of formation, and you got to be 1 mole of the substance from its elements, everything in standard states under standard condition. So ClF3 there is formed from Cl2, is formed from F2 because these are the diatomic elements of group 7. So I could have X and then the dot and cross of X, where I still have 7 outer shell electrons on each of X. I started with 7 outer shell electrons. I still have 6 more because I used 1 for covalent bonding already. These are what you call diatomic molecule from your IGCSE, GCSE, or O-level chemistry. Got to balance the equation. Cannot have more than 1 mole because the question specifies 1 mole of these. So you got 1 chlorine atoms, and therefore I need to put a half Cl2 in front. You got a 3 fluorine atom. You need to put 3 over 2 because a half times 2 give you 1 chlorine atom, and then 3 over 2 times 2 in the molecule, I get 3 fluorine atoms. And that's it for the 1 mark and overall 11 marks question there. Question number 2, which of these elements has the highest second ionization energy? This is a trick question. This is talking about second ionization energy. We're talking about X plus gaseous ion becoming X2 plus gaseous ion plus electrons. Typically, the highest first ionization energy will have been argon or neon because these are noble gases. So this one will have high first ionization energy. They are at the end of their period. At the end of a period, they should have the highest first ionization energy. But we want the second ionization energy to be the highest, so you can think of the answer being sodium. That's because when you have sodium, you have 2, 8, 1, and then you go to Na plus, then you have 2, 8, and that means in sodium now, this is looking like a noble gas, so it behaves like a noble gas electronic configuration. So that means it's got fully filled outer shell, and therefore it's going to be the most difficult to actually remove from this inner shell now. To become Na2 plus and 2, 7, you have to remove from this inner shell. Magnesium has got 2 outer shell electrons. Remove the first one, the next one is still removed from the outer shell. Neon and argon, they both will have very high first ionization energy, but then the sodium is the one that will have the highest second ionization energy, because if you look at neon will be 2, 8, I think, and then this is going to give you neon plus, which is 2, 7, and then neon 2 plus, which is going to be 2, 6. So here we are removing from the same shell, so of course it is still going to be, actually I might be mistaken. Let us just analyze this first. I know the answer cannot be argon because argon is from the third period, so period 3 will be slightly more difficult to remove. Okay, I might have to check back what I just said there. We're looking at Na plus versus Ne plus. So having said that, what I can do is I can compare the number of protons and electrons, sodium plus and Ne plus. So in terms of the protons, I have 11 protons, I have 10 protons for the neon. In terms of the electron count, I have 10 and I have 9. So this was removing from 2, 8, this was removing from 2, 7. So I think the highest would have been this one, because you are really taking it away from the noble gas configuration, whereas the first ionization energy, neon will be the higher one, but for the second ionization energy, sodium plus will have the higher one, simply because you are taking away from the noble gas or the fully filled outer shell electronic structure there. In the next part of the question, so I better move this thing around a little bit so that I'll have some more space. Nice, all right, don't worry about it. Okay, so this is asking you about atomic radii, and they are saying that it gets smaller from sodium to chlorine. So across a period, what actually happened? So it's a similar essay from earlier where I've talked about the highest first ionization energy across a period, because it's the exact same essay. The first point is the same, the second point is the same, the third point is the same, but we're going to relate it to the atomic radii here. So you have more protons in the nucleus, so number of protons increases across a period, so nuclear charge increases. So the positive charge inside the nucleus will get more and more positive. But then we also have shielding, which is roughly constant. And this is a result of you filling in the same shell as the electrons are filling in the same shell, which is the third period, so the third shell here. So the overall net attraction, and this is attraction between your outer shell electrons, because that is what governs your size. So outer shell electrons and also your nucleus, this attraction will get stronger as the thing that's blocking you is about the same, but you got more nuclear charge and more electrons on the outside. So therefore, size decrease, size, or you can say atomic radii, will get smaller and smaller as you pull the outer shell electrons closer to the nucleus there. Next part of the question is asking on the melting point. This is on S8 versus P4. So we knew earlier that the melting point was a question that we covered earlier. The metal goes up, sodium all the way to aluminium, and it goes all the way up to the silicon. It comes all the way down to the phosphorus, but then it rises up slightly to the S8. The P4 was lower than S8, and then Cl2, and then argon at the very end there. So in the end, we're looking at the total number of electrons in the molecules. So both S8 and also P4 have simple covalent structure. So it's always about structure and bonding. So because you have simple covalent structure, so we break only weak intermolecular forces, and in this case it's an element, so there is no permanent dipole. So specifically what we are breaking is just the temporary or the induced dipole. Temporary, I should really spell it properly, temporary or the induced dipoles, what we call the van der Waals. And the van der Waals essentially will get, so the van der Waals get weaker from van der Waals in S8 is actually stronger, sorry. So S8 is stronger than between P4. And what is the reason? The reason is due to the total number of electrons, as S8 has more total number of electrons. This has got nothing to do with the outer shell electrons. It's to do with the total number of electrons in the molecules, and therefore giving you stronger van der Waals, stronger induced temporary dipoles, and therefore require more energy to break. Therefore needs more energy to break. And if you need more energy to break, your melting point is slightly higher for S8 compared to P4 there. In part C, why does sodium oxide forms an alkaline solution? Well, I can write equation number 1. That's the most important thing. Write equation, write balance equation. You get NaOH. Alkaline solution, that means you have OH minus, and we got to balance our equation. So there's 2 NaOH there. So we can say that, well, Na2O is a metal oxide, and most metal oxide are basic oxide. So not all, because metal oxide such as aluminum oxide, they're amphoteric oxide. So majority of metal oxide are, however, going to be basic oxide. They form alkaline solution when they react or dissolve in water. Last but not least, question number 4. They want an ionic equation, not a simple equation. And this is between phosphorus 5 oxide. So what you have there is non-metal, but the valency is 5, the valency there is 2. Valency is what you call combining power, and here I'm just trying to get the correct chemical formulation where I exchange the valency, and this is labeled as how many. So we know P2O5 is basically the empirical formula of phosphorus 5 oxide, of which the actual molecular formula, the actual number of atoms in one single molecule, is actually going to be P4O10. So whether you use P2O5 or P4O10 here, you should be all right here. When you react it with sodium hydroxide, what you get there? Well, you will get a salt. This is phosphorus plus 5, according to the 5 there. You're going to get PO4 3 minus salt. And that is because in the PO4 3 minus, you have minus 3 charge. Phosphorus is the oxidation number you want to find. Oxidation number, the charge that an atom will carry if you form an ion. Oxygen is very electronegative. When you form ions, when it's bonded to here, oxygen is going to take away the electrons and give you a minus 2 charge. There are 4 of them. Sum up the individual oxidation numbers, you get minus 3 there. So phosphorus is minus 3 plus 8. Phosphorus is plus 5 there. So again, we are doing an acid and base neutralization reaction. So there is no change in the oxidation number. Your objective is to form the salt. The salt is Na plus, and therefore you're going to balance out the plus 1 and the 3 minus by having 3 of the plus 1. So Na plus, Na plus, Na plus like that. So you're going to get Na3 PO4, and you're going to get H2O. However, sodium salt is soluble in water. You can balance the equation. I forgot that it's between an acid and an alkali. When it's between an acid and alkali, there is only one ionic equation, as you have learned it from IGCSE. H plus from the acid plus OH minus from the alkali, giving you H2O which is the product in this neutralization reaction. So long story short, identify that it's a neutralization and there is only ionic equation for this neutralization reaction, H plus OH minus H2O liquid there, for that 1 marks and 7 marks overall there. I was just waffling along with all those formulation and stuff. All right, so that's it for this short tutorial. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel, and do follow me at ptet.chemistry. That's at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected, to get in touch if you're interested in personalized one-on-one tutoring where I can go through concepts or any questions of your choice. See you in the next tutorial video.